be providing a very simple introduction to neural networks, and then also talking a little bit about gradient descent. So a neural network essentially predicts new values based on input values. So for example, in the case of image recognition, you provide the neural network with an image or all of the pixels of the image, and it predicts a label of the image. So it tells us what the image is. In the case of text prediction, for example, you would give a sentence to the neural network and it would predict your next word, for example. So why do neural networks work so well? Well, they allow us to approximate very complex relationships between data points. So it allows us to approximate almost any non-linear relationships, so not just linear relationships. The more hidden neurons you add, or the more hidden layers you add, the more complexity is introduced to your neural network. So let's start off looking at the components of a neural network. Neural networks compose of different layers. Traditionally, you have an input layer, one or many hidden layers, and an output layer. So that is for a simple model. You can have models with more input layers or output layers, but for my purposes, we're going to stick to one input and one output layer. And for my demonstration, also only one hidden layer. So each layer consists of neurons. So here you can see the input layer consists of 3 neurons, the hidden layer consists of 4, and the output of 2 neurons. Each neuron has a value associated with it. Then each neuron is connected to all of the neurons in the next layer, okay? This is also for more complex models, it isn't necessarily the case, but I'm looking at a fully connected model, so everything is connected. So we will see all of the input neurons are connected to all of the hidden neurons, and all of the hidden neurons are connected to all of the output neurons. Each connection has weight associated with it. And each layer, except the input layer, has an activation function associated with it. For my purposes, I use very simple activation functions, ×2 and -10. In practice, we have a lot more complicated activation functions. There's well-known functions like the sigmoid or ReLU function, but for this demonstration, I'm keeping it simple. Those specific activation functions that are well-known are also appropriate. They've already been found to be appropriate for specific types of data problems or specific relationships between data points. The purpose of an activation function is actually very important. It essentially activates, so it determines whether the value of a neuron contributes to the eventual output value, the final output value, and how much it contributes. Then we have net values, and you obtain your net values by putting your neuron through the activation function. But we will have a look by, I will show you how everything works with an example. So how are all of these components connected? So in this example, we only have 2 input neurons and 1 output neuron. We have an input value of 2 and 3, and I arbitrarily chose some weights. Okay, so as you can see, we don't have the values of the hidden neurons or the output neuron. We're going to obtain them now. So if we look at the value of the first hidden neuron, how we get that is you take the value of the first input neuron, you multiply that with the weight of that's associated with the connection between the 2 neurons. You do the same for the next input neuron, add them together, and you get a value of 11 for that hidden neuron. Then you put it through an activation function, so 11 times 2, you get 22. That's your net value. Okay, you do the same for the next hidden neuron. You do the multiplication, add it together, get a 10, put it through the activation function, get a 20. You do that for all of the hidden neurons, and that's how you obtain those values. Now, to get your output neuron, in this case, we only have 1 output neuron. You can have multiple output neurons, but we're sticking to 1 for now. All of the hidden neurons feed into this output neuron. So we're going to use all of them. But in this case, you take the net value and multiply that with the weight. And you add all of that together. It's only in the case of the input layer that there's no activation function, so there's no net value to use. All the other times you would use the net value. Okay, you multiply that and add it together, and we get a 70. Then you put that through the activation function, so minus 10, and we get 60. So that is how all the components are connected. But in practice, when you start off with your neural network, you only have your inputs and your outputs. So you only have your 2 and the 3 and the 60. So the parameters that you need to obtain or optimize are the weights. So if you have your weights, you can determine the values of your hidden neurons and your output neuron, right? So it's the weights. Then your activation function. If you have your activation function, you can determine all of the net values. And you also have to optimize the number of hidden neurons and the number of hidden layers. So I just arbitrarily assumed 1 hidden layer and 4 hidden neurons, but it could easily be more layers or more hidden neurons. You will have to optimize your problem until you find the amount that, that depicts the relationship between your data points the best. Like I've already mentioned with the activation functions, there are a lot of well-known activation functions, so it's generally not too hard to choose the correct activation function. So I will be focusing on how we obtain the weights. So we use a process called gradient descent. What is gradient descent? It's an iterative technique. So it's a repetitive technique where we work backwards to find the set of weights which will result in an output which is the closest to your desired output. Okay, so you already know when you start training a neural network, your input values and your output values are known. So you want to obtain the set of weights that will result in this correct known output value. The steps of gradient descent: first we assign weights, then we do a feed forward pass, then we do back propagation, and then we do weight update. And you repeat this process, because I said it's an iterative process, until the values of the weights no longer change. So we no longer update the weights because you have found the correct weights. You have found the weights that results in the correct output. Okay, so let's look at an example. I'm using the same example we used previously, where we started with an input of 2 and 3, output of 60, same activation functions. So we know that we need to get to 60, right? So that is our desired output. First step is assign weights. So I randomly, usually when you start off with gradient descent, you just randomly assign weights. There are methods to initialize just your weights in a more optimal way, but I just did it randomly for this example. Your next step is to do a feed forward pass. So that is what I explained in the beginning. You say 2 times 2 and 3 times 1, add that together, put it through the net activation function. You work out your whole neural net until you get your output value. So for the random weights that I assigned, we got an output value of 46, but we know that's not right. We know it should be 60, right? So there is a difference between our target output and our actual output. Okay, so we know our weights are wrong. We just don't know yet by how much and how to fix it. Okay, so the error is called the difference between your target output and actual output is called your error. We usually make use of an error function. In this case, I chose the function of target output minus actual output squared. This is quite similar to a well-known function, which is mean squared error, but for now, I just made it a bit simpler. There are also a range of well-known error functions that you can use that go well with certain activation functions and are best suited to specific types of data problems. Okay, so this is what our error function looks like. It's a parabola. We, with our 46 that we obtained, we are on that side of the parabola. We want to be at the bottom. Why? Because we want an error of 0. We want our target output to be equal to our actual output. We know that the value that our target that our actual output should be 60. So how do we get there? We make use of a technique called backpropagation. So essentially what we're looking for is the slope for a specific weight, okay? How we get that is we differentiate that target output minus actual output squared. So we differentiate the error function, but with respect to a specific weight. So for the purposes of this demonstration, I'm going to focus on one weight, that 2 there. Usually you would take all of your weights simultaneously in a vector and differentiate, but that's going to take very long. So I'm not going to do that today. I'm also not doing the differentiation right now. I'll just tell you that the slope is -2. Okay. Step 4 is doing the weight update. So you take your to get the new weight, you take the old weight. So the weight used to be 2, and you subtract the slope that you got from it to get your new weight, which is then 4. Okay, back to step 1. We assign weights. So that weight that used to be a 2 becomes a 4. Step 2, we do a forward pass. Okay, I'm not working out everything again because we only changed one thing. So only your output value will change, and it's changed to an 80. You put it through the activation function, we get a 70. Okay, it's still not 60, it should still be 60. So we still have an error function. This time we're on this side of the parabola. Okay, so we overshot. We still need to get to the 0. So we do backpropagation. You get the slope once again. You subtract the slope from the old value and you get 3 for your new value. Okay, here we go again. You put it in again. And you repeat this process until you get a slope of 0. So until the slope of your weight is at the bottom of the parabola. So your error is 0. You are getting exactly the output that you desire. So you would see this start to happen when your new weight is equal to your old weight, because if you subtract the slope of 0 from that, they will start to be equal. In practice, you probably won't get a slope that's exactly equal to 0. You would probably get something quite close to it. So your new weight and old weight, the values will start to converge. And you usually want to stop training your model a little bit before. You don't want your new weight and old weight to be exactly equal to each other, else you're going to overfit your model. So you stop a bit before that. Okay, so now that you found your weights, your model is trained. And now you can use your model to predict outputs. So you can use your image recognition model, feed it some pixels, let it tell you what's in your image. And yes, that concludes my talk. Thank you so much for listening.